All right, welcome back everyone. Let's continue. Today I want to dive deeper into the differentiable simulation topic itself. As a quick reminder, who remembers what we talked about last week in terms of the loss functions? I hope you remember, right? We talked about first 2 weeks ago, we mainly focused on the data part, the supervised learning. And let's stick to that naming scheme. Last week we focused on these loss terms. Who remembers these two distinctive or the two different approaches that we talked about last week? Yes, yes. Sorry? Yes. Yeah, right. What was the difference? Mhm. Yes, to recap, right, that's a very nice summary. So we have pre-computed data for supervised and these physics residuals being evaluated for the loss version. We also talked about two variants of that loss. That's a bit more subtle. Who remembers the difference between the two ways these losses could be applied? Because it's conceptually, if you implement it or even just want to use it, there is actually there was a big difference in the two versions that I explained last week. Who remembers? The slides were called version 1 and version 2. Any idea? I mean, where was the solution? Does anyone remember where the solution? Right? We looked at things like a flow field as a target, where the solution was stored or lived for the two variants. One of them had in one of the cases, it was in the network basically. 50-50 chance. Right, so basically that was the version 2. For version 2, we have the network that essentially represents or stores the solution, right? If you call your network for one location, you actually get the velocity. And then the big question is, how do you evaluate the physics loss for each of those? Right, so one, the solution is a network. Physics loss, a PDE needs derivatives, right? Space or time or so. So these need to come from the network. So also the PDE or these derivatives were evaluated for the second version with the network directly, whereas in the other case, the solution external, right? So it's not in the network, so also the derivatives need to come from somewhere else, and basically constructed with classic methods, finite differences, or something like this. Right, so I think that's, or I would recommend to keep that in mind, or if that summary was sounded weird or unfamiliar to you, to take another look. That's a more important distinction. Right, so one time we have a solution basically in a grid or some external explicit storage in a computer. The other case, the solution lives in the network itself. If we want to evaluate the PDE is in a way the same, right? Can impose the same constraints on both sides. For the physics, it shouldn't matter too much, but we somehow need to formulate the PDE one time with these explicit representations, one time with the neural network. And on that front, suddenly there's a big difference. Today, I want to continue along this line. So the distinction is important to recap, because today I want to focus or go ahead towards these kinds of residuals and the constraints. And now we want to look at full simulations. We kind of expand on that scope. And that is actually more in line with the first approach. Because intuitively, if we have a network being the solution, it's in a way actually more difficult to impose these constraints. And try to with the goal of bringing together classic techniques and the neural networks So we can use a neural network, but then many of these classic techniques don't work anymore. I hinted at that last week already. Whereas if we have a regular simulator with an explicitly stored solution, we can use a lot of the techniques, actually still bring in a network. So that's going to be the main goal. And I should warn you right ahead, with these differentiable simulations, as we call them for this course, there is actually, for today, going to be quite a few equations and a bit of theory to set that up, to explain how it works, how the integration turns out and can be realized. And then we come to some examples, and I'll also explain how that works with some specific examples. But just to warn you ahead of time, we'll have some, at least on first sight, quite lengthy equations that we need to go through. But I hope at the end of the section, actually, you'll have a more of an intuition for what hides behind these expressions. Let's start with our basic setup. So we have a simulator. Actually, that is in a way just like before, right? So we have our PDE, whatever that is, flow, heat, right? Something. It's quite abstract for now. And we now can formulate some residual, this one we used before, and turn this into a simulator. So just based on the exact same formulation, that's actually very easy. You could just take this time derivative and integrate it in time. We could do Euler steps, right? Or we could put anything on top that basically evolves the time evolution of our states u with that derivative. And then suddenly, from that one residual, you would get a whole sequence over time. So that would turn this residual formulation into a full simulator. And the main idea now is to use such a simulator in a way not doing much more than exactly computing these derivatives and the time integration and combine them with a neural network. So now we have the simulator that computes these residuals and we have a neural network. Right, so before we actually tried to basically train a network to learn from these residuals, and in a way then after training the residual didn't play a role anymore. It's really just was there for training. Afterwards, we could forget about it. And now we keep both. So both our simulator, right, typically will still be called P now, and the network will live on and be present in training and at inference time. So they'll stick around. That's an important distinction. Compared to before, right, we can actually borrow quite a bit of the formulation. And in a way, the picture is also similar. The main difference is now that we actually still need to be able to derive these physics terms that we have. Mostly in this case, we actually focus on this P function that now encapsulates both time integration and the spatial terms. And these residuals and the directions we get from that solver now should work together with our neural networks later on. But in a way, you can see those as two separate steps. So one step is actually being given some physics function. We want to compute these gradients, these directions from them. And the other one is then taking those directions and putting them into networks or using them for training. And because it's actually nicely separable, we first look at how to compute the derivatives. So writing that out in a formulation, that is the partial derivative of our function or simulator function P with respect to our states U. So in a way, just a derivative written here in a slightly less intuitive fashion, right? You could traditionally imagine there's a dash or so somewhere, or if this would be time, you could write it with a dot, but the main idea here is that these states are partial. There are potentially other parameters in P that we do not include, but we restrict ourselves, right? We have a multivariate function. We restrict ourselves to a subset of the variables that are necessary for time evolution or for the steps we are interested in. And then if you think about what happens here, right, the u has multiple terms. It could be a velocity, x, y, z, could have 3 terms or so, or you could have a whole grid of velocities, suddenly it could be millions. It actually doesn't matter too much. But both sides of the equation and basically both of these terms have multiple variables, and this is actually a matrix. This is a Jacobian matrix. Both are higher dimensional. If we would be in 1D setting, it would be a single number, right? A matrix reduces to one number if it's 1 by 1. But in the most usual case, we'll actually potentially have a pretty big matrix just for this term. And that's going to be the goal of the next couple of slides, how to compute these terms and how to work with these Jacobian matrices, because that's going to be a crucial ingredient. In a way that already played a role last week, but yeah, you can actually get away with less detail if you just push all that to the loss side. If we now really want to work with the tighter integration, it's worth looking at more of the details. All right. I do want to comment briefly on the name here. So we'll call it, right, differentiable physics. There are all kinds of names you'll find in literature. It's not well standardized. It's a pretty dynamic field, so standardization is not one of the strengths of science, but right, people stick to the way they're used to or they like to call things. Hence, you can find all kinds of names that are not fully standardized, right? Physics, also constrained or based or augmented. The physics informed moniker, that's typically associated with these neural networks. So that's a distinction. It's not physics informed, but other physics. And it is also, if you look at the classical literature, quite in line with the joint methods. Essentially, adjoints or adjoint optimization focuses on quite a few ideas that align with the training that we'll discuss here, bringing in simulators. So if you come across adjoint methods or quite a few techniques from the adjoint field are actually applicable in the context of learning. Essentially what we're doing is we're backpropagating through the simulators, which also is, if you look at it, this reverse mode differentiation to distinguish from the forward mode, which in this case is typically less attractive because we have the scalar loss functions at the end. So, right, all of these essentially mean the same thing, and we'll stick to this differentiable physics name in short, typically also to distinguish it because from other differentiable processes. So you could imagine that we have there are financial models, or it could be a crowd, or you have rendering light simulations that are differentiable. By now they're in the learning field actually quite a few of these differentiable operators. We'll mostly look at differentiable physics operators, hence the name differentiable physics. But the larger field, good summary would probably be this differentiable programming field, which if you think about it is actually an interesting aspect of the whole learning algorithms, because that's also what happens in a normal neural network, right? Every layer, every component that we have for a neural network, whether it's a conv layer or an activation function, so they need to be differentiable, otherwise you can't backprop through them. So essentially, when you're using PyTorch or so, you're setting up a computational graph that is differentiable, that you can go forward to compute a result, but you can also go backward to compute the gradients, right? That without that, the learning wouldn't work. So that lies under the hood of all these deep learning frameworks. And some people have started to summarize that as differentiable programming, because effectively that is what happens in many of these frameworks. Yeah, also a very interesting topic, but a bit beyond our scope here. So just good to keep in mind. How do we now get there? How can we apply these simulators in the context of such a computational graph? And who's come across Jacobian vector product or the kind of the functionality to compute Jacobian vector products in some deep learning framework? Has anyone looked at that? Or Others, yeah, usually it happens quite a bit under the hood, but it is actually a super important operation in any of the steps that we traditionally use. Right, you could argue, well, luckily, normally we don't need to deal with it too much, but if you now want to understand how it should work for simulations, or if you in the future want to set up own simulators that support this, it's important to know what happens here. So what is meant with Jacobian vector products is the idea that we have a sequence of operations. Say we have m operations, doesn't matter what it is, right? Could actually be a convolution or a dense matrix multiplication or just an activation, or a matrix multiplication associated with the simulator. Any sequence of m steps, now in line with our, keeping in mind that we want to go towards physics, called Pm to P1 here, applied to our state u. I've written now on the slide here explicitly also some other parameter in nu, for example, for some viscosity. So just to write out once, potentially our simulator could depend on other things. This is really just an example, could be at any list of other parameters. In practice, all kinds of hyperparameters and other things that influence what comes out of this P that are not explicitly part of the state. Typically, those don't play a role so much, but just to remind you, these are typically inputs to our simulator. And now what we're interested in are these derivatives of our simulator output with respect to the input. And that's a matrix. So that's important to write out and keep in mind here. This derivative that I also had on the previous slide for some of these operation, or any operation I in our chain, is now derivative of P with respect to U. And both of them, if we now focus on U, have potentially all these different dimensions that U is storing. In the end, it's fairly simple. We are simply now looking at the ith operation here in the first component of P and the derivative of that first component with respect to all the outputs. So U1, U2, U3, until, in this case, UD for a d-dimensional vector U. So that's the first row, and the second row, the same happens for the second dimension of P, and so on, all the way till the dth dimension of P. In this case, both P basically takes one U as input, produces one as output. So we are dealing with a d by d matrix here. In the general case, also actually often in deep learning, they're not square, but for most of our settings, input-output of a state, we can or will have a square Jacobian matrices here, although right, we actually don't need that property too much. So keep in mind this could be, if you have functions that map to different dimensionalities, could be non-square. But yeah, ultimately it's really just a bunch of derivatives in a matrix. All outputs with respect to all inputs. And then in this form, it looks a bit unwieldy, but yeah, it's in the end also, these are all just first derivatives. So if you go through the equations, all you need to do for each of these is basically compute one derivative, but you need to treat each of those components separately. Now, just to have it on the slide, we could, of course, also compute the derivative of our P with respect to the nu, this viscosity or so. We assume we don't need that. For other cases, you might. There are inverse problems where you actually might want to figure out, say, viscosity value. Then, of course, we need to compute this. But even in this case, you probably have other parameters that you don't want to compute a gradient for. So this is just an example of some quantity that we'll neglect in the calculation of Jacobians. And also what's important to keep in mind is this is the Jacobian for one of these operations in the big chain up here, or m steps in sequence. If we now want to treat all of these, it's basically just a chain rule. So what happens if we have just two of these? So now looking at this part down here, so if we just take P1 and P2. Now assuming actually we first apply P2 to some input, then P1, then we have a chain rule. So effectively we need to multiply, well, chain rule as you know from school, I'm sure f of g of x derived is actually the outer derivative for f times the inner derivative. That's exactly now what happens with the Jacobians. We first compute a Jacobian for g or P2 here, which would represent the g in this example. So here on the slide you can find the derivative of P2 with respect to u. This is again this Jacobian matrix. This now, according to the chain rule, needs to be evaluated at the position or at the state un, assuming this is what went into the calculation. And this whole matrix, so keep in mind this expression now, it could potentially, well, our example is a square matrix, other cases could be a non-square one, is multiplied with the Jacobian of the of this P1 function that we're applying here. This now is evaluated at the position P2 of u. And in our case, both are square multiplied. Well, you can imagine it basically. And we have two square matrices being multiplied by another vector of the same size. So it's all dimensionality d. Even if we had different dimensionalities, because in this case P1 would be called on P2, the dimensions need to match. So these outer products of the matrices always need to align if you go through it. Otherwise, we couldn't call one of these operations onto the other one. So it's relatively clear how the matrices need to be shaped. But in our case, it's especially simple because the size of u, this d, actually propagates through all of them. If we multiply these two Jacobians together, then we actually have the joint derivative of the sequence of operations, in this case the P2 and the P1. And you can imagine now what happens if we have a longer chain like the one here at the top. We actually just get a few more terms. So we just get more of these Jacobians on the left-hand side for all the additional ones. So simply becomes a stack of matrices that are multiplied one to the other. And that's exactly actually now what happens in all of your deep learning frameworks. And to come back to the title of the slide, the Jacobian vector products, the trick in practice is always, for all of these deep learning frameworks, that we actually never need to construct this whole Jacobian matrix. Potentially, we'd like to deal with complex things, right? This D could be 1,000,000. It could be huge. We don't want to store 1,000,000 times 1,000,000 matrix, especially not many of them for each step in our chain. But what we always rely on is that the final operation, the final target for all of these is this loss function. And it's not a coincidence. There's always a single number. We're always reducing, no matter how complicated, all the steps before, we're reducing it to one single number. And from this single number, we're starting the backprop step through the whole forwards chain. And because this is just one number, the Jacobian of the loss with respect to u, here written out, so the partial L, partial u, right, u now standing for any quantity that we might compute. This is now, because loss is scalar, if you think back, oh yeah, here, I still have it on the slide, exactly, to the expression at the top here, now shown in pink here, right? This is our Jacobian. This, of course, we also need to compute for the loss, but our loss just has one dimension. So what's actually left now is simply just one row of this Jacobian. And in practice, by convention, what we're typically looking at is a transpose of that to turn this row into a vector, and that's your gradient vector. So this quantity, the Jacobian of the loss, this is the gradient vector we're typically dealing with in all these optimizations and learning frameworks. And this is what always comes out at the very end, because our loss is always a number. And this is now great, because we can rely, we're guaranteed to have a single number at the output. So we don't need to store a matrix in this case. It's really exactly just a vector on the size of the outputs of the previous step. And that means we don't need to store these matrices, but we can always rely on contracting the multiplication by this Jacobian with a vector. So we can always map it to the size of the output of an operation and basically sum over the dimensionality of the next step in the forward chain. Let me just draw it out, right? So we always have our Jacobian matrix and an incoming vector. And now if you compute the matrix multiplication, right? So for one row here, right, we multiply all the different components, but what comes out here is guaranteed to be one number. Right? That happens for every row. So the output here will be just a new vector. And typically that's what all the frameworks do. They do not construct this whole matrix, this dense matrix, and compute this incoming gradient vector times matrix as a matrix vector product, but they typically have very efficient implementations of computing just the accumulation of all these terms and storing just this one vector as an output. Otherwise, in practice, right, many of current approaches and setups would not be feasible, would blow up in terms of memory. Because yeah, if you think about it in the backprop step, we typically just need to do this once, and we are not really interested in all these entries in the Jacobian. We just need to compute the gradient for backprop, but then we can forget about it. We need it once, we need the result, and this goes into the next step. Right, this vector now is multiplied again with a new Jacobian matrix from the forward pass previous step, but again, it's multiplied by this one vector, and we get a new vector coming out, and so on. This goes into the next one. So we never need more than a vector, and this is crucial for this being feasible. So in the general joint picture or general optimization framework, right, this could be higher dimensional. You could have something different than a loss, but for all learning and in all the current frameworks, this is really a crucial ingredient and important to make it work. And, right, wrong story now. This is, of course, also what we need for our simulations. If we have a simulator that performs operations, we need our simulator to provide the Jacobian matrix, or even better, some efficient way to compute such a Jacobian vector product. If we have this, then we can actually backprop some information through the simulator efficiently, and not all simulators have this. So this is not to be taken for granted, but I think it's getting there, it's improving. This is potentially a pretty important decision or core capability for a simulator to be coupled to learning or not. Yeah, so I do have it written out here on the slides. If we now go back to our full sequence of m steps in our simulator, then right, for the whole derivative of our solver, we basically get this whole chain of Jacobians. Theoretically, you could construct each of those, treat them as a matrix, but what now actually in the context of all the deep learning frameworks and probably even beyond is a pretty good idea, is to treat those as a sequence of Jacobian vector products relying on a single vector coming in as a very last step. So here I've omitted the loss again. This is just for the solver itself, and resolve this sequence of Jacobians by relying on a backprop that contracts each of these to a single vector. And basically for each of these operations, one by one, make sure that in our simulator we have some efficient function that takes the incoming gradient from the following step in the forward pass, computes the multiplication of the current derivatives with that incoming one, and then outputs the gradient vector to whatever came before in our forward pass. Right, so remember, this now goes back propagating in reverse order of the forward steps. But yeah, this is what the frameworks like PyTorch track internally, right? They have this whole graph of steps that were active in the forward pass. So typically this is relatively easy, or you could imagine it's a tracking of operations, and then we need to unroll that. We need to go back one by one, basically call some suitable function to give us the multiplication of the Jacobian for that function with some incoming vector, and then that is passed on to the next one step by step. So essentially, it's a list that is built in the forward pass, and then we go through it again in the backwards pass. This sequence really is one of the key steps for making simulators differentiable and for putting them into deep learning frameworks. Are there questions about this part? Is that clear, the main idea here? So we have derivatives for each of these operations. These kind of more optimized Jacobian vector, this view of just computing Jacobian vector products is in a way just already an optimization. Theoretically, it would be absolutely correct to just construct each of these matrices separately and then do a big sequence of matrix operations. It would be identical, would work. It's just a matter of scaling this up where it would break. Would probably have a lot of zeros and consume a lot of memory. So in practice, it's not a good idea, but it would give the right answer. The important concept is really this idea of building a chain of operations and computing Jacobians for each of them. The nice thing about this is also that it's quite flexible, right? So if I have any operation here, the P2, if I can compute the Jacobian for the P2 operation, then I could use it in another context. I could just use P2 by itself. If I can get the Jacobian, I can actually put this into an optimization. I can do learning with it. We could easily switch the order of these operations. So this viewpoint is actually a quite neat one. Again, in the context of classic adjoints, the alternative would be to basically write out expressions for this whole chain of operations, compute derivatives of output with respect to input for exactly those operations, to kind of compute all this jointly, and then might have a suitable solve or a way to compute these in one go. That is a classic joint picture, but in a way it's actually restrictive, because you need to do this for exactly one chain. You need to resolve this. It's non-trivial, so this gives you quite some flexibility and a way to break down a fairly complex operation. Right? This could be now a whole plasma physics solve or a blood flow model or something, and you could break this down into different steps, have some flexibility, also develop this operator by operator, and it actually very nicely plays along, making it integratable or for coupling it with the deep learning framework. Yeah, so that's the main. That's basically the core idea behind these differentiable simulators. And so far, I've not been given any specifics for what we're actually dealing with physics, what this P operator actually does. So I want to catch up on that front and show how that works with a fluid simulator as an example. So for fluid simulations, some of you came across that in one form or the other. We basically to solve the Navier-Stokes equations. That's what they look like. Important to have them on slides at least once, I believe. But even if you're not familiar with that, I'll basically give you one way, one of the simplest way of actually solving this. It's an own field of science, basically. So there are many very advanced techniques, but if you use the very simplest approach, you can basically look at each of those terms separately So basically each of these terms in the actually two equations up here, and these the material derivative on the left-hand side here, that is basically accounting for the transport. So things like the fluid or air or so moving around over time. The other ones are essentially can be seen as force terms. And if we look at each of these separately, it's not super accurate. It's first order in time, but it actually solves in the limit, things being small enough, the Navier-Stokes equations. So here's a small breakdown. Right, this first part here, that's the advection step that accounts for transport. We can solve that by itself. The second equation, that one accounts for the conservation of mass enforcing divergence freeness. And then the viscosity term, which is this one up here. This is basically a diffusion term, so I'm actually blurring things like the velocity out a bit. This is what we'll neglect, because in practice, especially if you have not super accurate solvers, they actually introduce diffusion. It's like viscosity. So with a simple method, we have plenty of that, or more than we want, and we don't need to spend additional effort to compute this term. If you would want to be more efficient and go for very turbulent flows, then this actually, or very viscous ones, that would be an important contribution. But right, it's basically another linear solve, a bit similar to the pressure projection. So we are focused on this advection part, forcing divergence freeness, and then this goes into the P, potentially some additional forces. So let's look at the first part, this transport. What we, as an example of how to get basically a differentiable advection step, what we can look at as a problem that explains the main ideas is if we now take a passive field, something like a smoke density, that should be moved in a flow field with some velocities u. So what we'll now assume our P does, right, so keep in mind this P is a general term for any physics model. In this case, it will account for transport, not the other bits for this and the next slide roughly. So this P operator now takes a density d at time t, this velocity field, and gives us a new value of this smoke or this marker quantity at the time t plus delta t. Essentially, what we're solving with this is the following equation. So the time derivative of t being velocity dot the gradient of this d. But right, if you then discretize this, if you compute this with simple schemes, what you get is a so-called upwinding scheme. There are alternatives here, but I want to focus on this upwinding because I think that's quite intuitive. So the basic setup here, just to have it on the slide, in this case is we have some marker quantity, right, it could be a blob of smoke. We have a velocity u here in the middle. This is assumed to be constant for the step. And that moves around our smoke. So for example, might blow it up here a bit, and then what should come out is this moved marker quantity on a grid. This might sound a bit or look a bit artificial, but this is actually a pretty important process. We've used that extensively. So one example is our scalar flow experiment that you can see on the video already. So what we did there is actually very simple very much in line with the toy problem I'm going to show. We have small quantities, right? You can see it on the video. There's just a small fog machine in this case that is a bit controlled with the temperature, has this rising fog. And then this is filmed with a bunch of cameras here on the side. And the research goal there was actually also really to find the u, so the motion that drove the evolution of these marker quantities. Just to give an outlook, this is now very reduced and might seem artificial, but it is actually a quite challenging problem that you might encounter in the real world. So what we are now looking at is we have such a density, we have some target here, exactly like just shown, right? You might take photos or 2 photos of this rising fog over time, and we want to now start with a initial density called du, evolve it with a flow field such that at the later time, Te, it matches the target. In our formulation with our advection operator P, our velocity u, this is basically the learning goal here, or the optimization target. And if you now write this out, also as before, what we now are looking for to compute the velocity is in the context or in the perspective of typical learning, gradient descent, a step in terms of the velocity u, so right, delta u, that comes from the loss, right? Loss being this expression up here, the target density minus what came out of our advection step, out of this P, that should match. Keep in mind, so we're putting in the du, we move it around, and then the moved d should be in line with the target, meaning our loss should go to 0 ideally, or be as small as possible. So to find u such that these 2 fields align, the loss just compares these 2 d fields, and this loss is then basically here computing this gradient. Mentioned before, this is Jacobian, but it goes into a single vector, and here this term now multiplies that with the Jacobian of the advection part, and this is what gives the final step in u. Yeah, so if we now resolve these 2 steps, in this case our whole chain of operations for a whole solve is basically just the 2, or the loss and the advection step. And the loss in this case is a quadratic loss. So if you compute the derivative of that with respect to our density, so it's written out here, right? So Jacobian, in this case, we just the derivative of the loss for such a squared loss is quite simple. It's just the difference of the velocity of the density of this marker field that comes out minus the one at the target, and from the you can see it as 2 functions, the inner derivative and the outer derivative, and from the outer one we then actually get another factor of 2 here from the square. But the main ingredient here, or I hope also the main important quantity, is basically how much or how well does this density, the density that we computed in our advection step, match the target, right? So this is potentially, you can see this as a long vector of values, but you can also imagine these being arranged on a grid, right? So basically this tells you the difference between two quantities on a grid, 2 shapes. So ideally, if we have one of them being here and the other one being here, it actually doesn't matter too much which is the target or the other one. Then if you take the difference of these 2, right, you would probably get 0 values in the middle, but you would get, right, depending on your sign, you would see an error in the parts where these 2 shapes don't align, right? So you would see the mismatch of these 2 shapes. This is really just an in-place difference of the fields. This is the Jacobian, the gradient of the loss, right? This is actually what comes out of such an L2 loss. It tells you where did my target go wrong. So typically what's also important is here a plus or a minus sign. So in this case, depending on how you set it up, would be on one way, but that is an important information here, not only, right, here there's some variable, this could be in a grid some value of our dij, and it's important for the optimization to know this value of d was too large, it was too small, right? That is basically the crucial information that comes out of such a L2 loss in the very last step. Should my value go up or down? And by how much? Their variance. If you would use L1, you would just get the direction. With L2, you also get actually a factor for how much it was off. But arguably the most important information here you get is this value in my optimization needs to go up or it needs to go down. It was wrong by in which direction. So I hope this makes sense. The Jacobian of this loss for the scenario is really just a direction where each of these, in this case, density values are wrong, primarily in terms of the sign, and then also by sticking to the L2 loss, by the difference of the target, how far the density value was away from the target value. And this gradient vector we now need to provide to this advection step to then tell us, well, what should the u here have been to produce the right value of the densities? Right, this is now what needs to be encoded in the Jacobian of this advection step. How is the u used to change the d values? And in this case, what we're interested in, how do we need to set u to get the right values, to get these target values out in the end. So we now have the first bit, we have the Jacobian of the loss. So now we need the Jacobian of this advection operator. And that's a very good next step. But after all these Jacobians, I think it's also a good point for a quick break, unless there are questions. Yes?
So this
there was a question now, the P coming out of the neural network. That's a very good question, but no, we have no neural networks here. So it's a very good question because it's important to clarify. We have no neural networks. All of this so far in this chapter with the differentiable simulators is completely independent from neural networks. The P is only the calculation. It's actually an operation, a mathematical solve basically, that computes this motion. Yes, exactly. So finite differences, something along the classical lines of, I'll come to it in a moment with this upwinding, exactly. It's something that computes how these d values move around in a grid. But it's important to point out there are no neural networks here in this picture so far. You could couple it, right? And in the loss or so, in one of these steps, you could have a network producing the values of d or changing them. Later on, it will be quite easy to integrate. But so far in this example, so far we are leaving neural networks completely out of the picture. We're just looking at the solver. So yes, very important point. Yeah. Exactly. Later on, yeah. So the question was how this solver or the step would later on work along the lines of a layer in a normal neural network. There are actually a lot of different ways to employ it later on, but you can actually for now also keep in mind this advection step, which I'll go into details next, is like a layer that does something to an input, right? Like a conv operation or some, right? Anything, right? A square or activation function that you call on some tensor in PyTorch. You could also call this P on a tensor of d values. And then it should, in this case, actually give you some moved values. So, well, you could imagine that this P here basically in PyTorch would take, well, a U and a D, those two being tensors of the right size. And then the U would be interpreted, well, these should have two components, right, two directions, as as a motion and move around the values of d. This is exactly what we later on could do, and then it's also flexible, right? Later on, the d could come out of a neural network, or you could feed whatever comes out here back into a neural network. It's quite flexible then, because it's really just an operation that works like any other layer in a differentiable chain. Yeah. Yes. The question was, what is the goal of the whole backpropagation? Also good to remind, this is the goal. A step in U. So in this example, what we're looking for is the motion. So a bit like the previous example that I had with the smoke, we're looking at something, we're basically seeing these densities, and we want to find out and optimize basically how did it move. That's basically the question here. So we're computing a gradient, a step, a delta, with respect to these U values. The question was, I guess, a bit like the exercises we had. If you're throwing a ball, or we have a simulation of a ball, well, then RP would take the states of the ball. So then you would have all the positions and velocities of a ball. It's one ball, or it could be concatenated multiple ones, doesn't matter too much, and would give you the next time step of the balls. In this, well, actually, in this example here, right, we have the split between an observed. This example is slightly more involved to before, because here we actually have an observed quantity, the density, and one we optimize for. They're different. They could be the same, but with the ball example in this context, it would probably be more in line with observing the positions of the balls, and then optimizing for the velocity also of the ball or the balls. And with the balls, I mean, a lot of the dynamics would come from gravity and acceleration, right? They don't, unless they collide, change too much in mid-air. So probably what you would be looking at for the balls would be an initial velocity. It could be a good question, right? You're observing a ball with different positions. It had an initial velocity that's unknown, and now over these different steps, or potentially 2 steps, we want to know what could the initial velocity of the ball have been, and compute it. And what comes out of this, now what I have on the slides, of this one process is just a step in U, right? So you would basically, with the current state, you would run your simulator with your ball ending up somewhere. You know from your picture it should be in a certain spot. And then the delta U would basically just tell you a certain step in the direction. Well, according to my physical model, I need to change the velocity up or down by this amount to get closer to that target. And typically, I hope you remember, right, all of the learning tasks and many of the simulations are nonlinear. It would be linear. We could actually make one step and arrive at the target. But in the nonlinear setting, we are just computing a direction, first derivative. We need to make multiple steps to actually arrive at the right answer. Sorry? Yeah. So in our picture here, because also I want to expand this a bit to multiple steps in a moment, we're assuming that P just computes one step from time t to t plus 1 or plus delta t. So you could imagine, of course, calling P multiple times to get further in time, right? So we could have P of P of P of some initial state U to go 3 steps in time forward. The same idea, right? These Jacobians, you would get a few more of these terms, basically, but same idea. Yes? to recap, your question is, the P represents an Euler step, and we're trying to learn the Euler step. It's correct, I think, from the idea, but I'm not sure what you mean with learning the Euler step, because keep in mind what we're learning is a step in this U. So in a way, we are not really, you could argue whether this is learning. We're just computing the values of U to explain what we observed. So we're trying to find a solution for U. You can call this learning for one data point. It's a bit more like a classical optimization. It's typically not what happens in learning, right? We have a big data set and we're trying to find a compromise for all the observed things. It's more basically computing one specific velocity, one solution for one specific case. Yeah, but you could call this learning. There's different ways to solve it. In this example, also with a step in U, we're basically solving it like a learning task with gradient descent to get one of these velocities. Potentially could even use different optimizers or schemes here. Okay, but good questions, right? I think this is important to keep in mind with the whole direction and what we're computing here. I think in a way, right, I come to it. Also, what hides behind these expressions is not too complicated in most cases. We've tried to simplify the also notation here, right? You could actually formalize this a lot more. As you really noticed, I didn't formally write out all the dimensionalities of the different quantities, right? Normally you would need to write each of these vectors or matrices is part of a certain R to the so-and-so dimensions. I've omitted that. It is, if you look at the details, usually quite clear, but it would expand all the notation by quite a bit more. And the formulations quickly do get quite lengthy. I think the more important bit also is to get a certain intuition and overview for the steps to be computed in the typical chain here. All right, so now let's come to this advection step. What I want to employ here to actually compute this motion is upwinding. Who's come across upwinding as a finite difference scheme? Okay, then it's good to mention. So this advection, right, this transport on a grid is a very basic operation for many simulators. And what upwinding basically does is, again, it's a bit ugly to write in terms of equations, but it just looks at how do I need to update values in a grid to compute transport. So what does it mean if I now have a grid here and so this should be x. I have a function I want to move around, then the question is basically I have a certain point here on my grid. Right now there's a certain quantity in green, that's a d, these densities that we might observe. What new value should be there if, say, I want to move the whole thing to the right or to the left? At this one position, well, all it does is go up or down a bit, right? The question is by how much, and should it go up or down? So what upwinding does is, it's actually relatively smart. If things move to the right, well, where do I need to look to find out what value should be there? I need to basically look back, right? Things moving to the right means I need to look to the left to see what arrives at a certain spot. In this example, right, I basically need to do a certain step and check what's the value here. And this value now should end up at this location in the grid. If the velocity would point in the other direction, and if things would be moving this way, what upwinding does is it basically looks the other way. So now I basically need to look for this step. Things should go down. And it's basically an if statement. It's actually quite easy to code. If velocity positive, negative, look left or right. It's a bit, if statements are not so nice in analytic expression, so a common way to write it is to basically do a min-max operation. So that's also what's done up here. So if you look here in this u plus, we're taking the min of ui, u is the velocity, divided by delta x, so it's kind of looking at the spacing in a grid. The minimum being if this is less than 0, we're stuck with 0. Which means if it's positive, so you say, easy to get mixed up. So it's taking the minimum of both. So if u is less than 0, we keep the negative values. If they're larger than 0, we take the minimum, it's all 0. So this does not let any positive values through. We're keeping negative ones, meaning u plus movement in the positive direction, we're looking at negative ones. And the u minus does the opposite. Here we're taking the max. So if the u becomes negative, we'll only see 0, no influence, basically clamped, or like an if statement. If it's positive, then we keep the u values. So this is basically an if statement for the sign of our u values. And these u plus, u minus values are now used up here to multiply a forward difference and a backwards difference. Right, and as you know, I can follow, the u, depending on being positive or negative, is 0 for one, the other value for the other one. So we're basically just keeping one of these two finite difference approximations. So we're looking at the gradient, first derivative, in this case of d, either backwards or forward. And that's what this upwinding does. And I have now to quickly remove the drawings. If you now plug this into our solver, so we now compute what p does, assuming a negative velocity. Well, for negative velocity, we are actually in this case, so we are in the u plus case. Then we have the expression up here. And this multiplies out to the values down here. So we basically we're left with the uy divided by the x prefactor, and the di here from the front also sticks around. So what we're left with in the end is down here 1 plus this factor from the velocity times di, and just this velocity factor di plus 1, or minus, the minus sign, and this gives us the updated value of our di. This expression here gives us the update for a negative velocity. So this is what our p does, right? So I hope you remember from before, we're basically interested in the Jacobian at the current position, at the current state of our system. So only writing out the negative velocity case is what would happen in a forward pass, right? We're not interested in the general expression now for any value of the u. All we need is the derivative of our operator of any of these pi steps at the state of our system in the forward pass. And right, if the velocity here was negative there, then all we need is actually the negative velocity case. Yeah. What's now necessary to compute the Jacobian of that is to actually compute the derivative of that function of our p operator with respect to the quantity we're interested in, which was the u. Right? So we are working with the densities, but what we're interested in is how did things move, and that's actually not too difficult now. If you look at this, there's a u in here. If we take a first derivative of that, all we're left with, right, the one drops out. What we're left with are basically these different terms that multiplied the ui in this expression. Right, that's what is summarized here in the Jacobian of our operator now for the derivative. In this case, it's actually quite simplified because we're just looking at one of the components of the velocity to compute the whole expression here. You actually would need to now do this for every one of the velocity entries, right? So this is 1D. Even 1D would potentially have more of these U values. In a 2D grid, for example, you would have all the 2D values and different velocity components. So you would have a lot of these factors, but each of them would probably not look very different. For upwinding, each of these would basically have either a positive or a negative step in terms of the D with a certain weighting by, this case, from the time step and the spacing, the dx. So if you think about it, if you look at this, this is now quite similar to a regular forward difference in the advection step up there, right? So now for forward difference, we'd have I plus 1 minus I divided by the step size. And now here we have I minus I plus 1 with some prefactors. But it's not so far from an actual difference calculation. And if you think about it, that's, I hope it's also potentially a bit plausible, right? Because that basically means, well, the velocity should take into account what the density values are. That's how it works in the forward pass. So if we now also want to find a velocity, we need to change it such that when we apply it, it actually works with the right values. So it's a bit like an inverted finite difference here, the direction we get, such that later on when we look at the forward difference, we have a U that moves things in the right direction. Right? So these Jacobians are not formally an inverse. They're not perfectly inverting what happened in the forward pass, but it's in a way an approximation. We're looking at the first derivative, and then we're going backwards along that derivative to essentially approximate what or how to change things so that things go right in the next forward pass. I hope that cleared out some parts of the whole setup, right? So it's, if you want to do this, it's potentially a bit tedious. You need to compute these derivatives for inputs, outputs. You need to check how were the values in the forward pass combined, and then make sure you can actually compute them once. But in the end, it's actually really just computing the first derivative of whatever was computed in the forward pass, and that you need to do for the backprop. Yes. But also, the question was, it's not an iterative process. Exactly. This is not an iterative process. It's also a good point. Potentially what could happen in the forwards pass is something that's iterative or more complex. Then you need to make sure you take into account all the steps that went into computing P. But in this case, it's a simple explicit step forward. So the backward step is actually also just based on these simple ones. I'll come to a slightly more complicated example in a moment. If your P operator is very complex and does a lot of things, it might actually be tricky to compute. If this hides a very complicated solve with many steps, what you typically can do still is you can kind of accumulate or collect all the things that happened in the form of the final gradient. But if this P is very complicated, it might be a bit more work. But I think for most steps that you encounter in solvers, it's actually not too bad. So I'll come also to the form of an iterative solver in a moment. First, there's one more complication that I want to talk about, is the multiple steps. We also had that before, right, with the ball simulator or so, right? We might not just want to do one step, but we might have any number of steps. I don't want to go for the completely generic case yet, but as a slight complication, which I think shows most of the concepts or most of the things that change in that setting, is let's assume we now have a sequence of these densities, our smoke that moves around a bit, and we're always applying the same U. That's of course actually not realistic for air or so. For a real system, the motion would also change over time. But let's assume we just have one U value that we want to find again, that we apply in many steps. And we observe here at the very end how it should look like, and then we try to go through all of these steps, repeatedly applying U. and we want to optimize for u. We want to find the value of u that explains what we had in the d values. So it's still simplified, definitely, because we're basically dealing with a constant u. In reality, usually will probably be changing, but nonetheless, it now has this complexity that now we have multiple of these steps. And what I also want to directly do is I want to change the loss a bit, right? So we actually want to apply this loss such that it does not only compute, or our sequence is not only computed at the very last step, but actually over each of the steps. So this is an important change now. So we basically have a loss that is now made up of multiple terms. Let's say in this example, we want to do s steps of these advection, of the advection operator, and we want to also compute s loss terms. So not just one final loss, but each step along the way, we want to compute a loss and minimize that target. That is actually also typically what we want to do later on in many simulation settings. So, right, you can probably imagine a bit. One of the core changes now is that we have s of these terms. Not just one match with the target, one L2 loss, but we have s. Drawing this out a bit, we have our initial state, the d, and then right we have go into our advection step. We have a new step. We do this our s times. Then for each of these intermediates and the final one, we compute the loss. And one important thing now to keep in mind is that we still don't have any neural network, but potentially in line with involving networks later on, we now have each of these terms over time that influences the velocity, right? So each of these steps, the green arrows with the p up there, uses the u. So if we now backprop through them, we get a contribution. We get a gradient here. Each of these changes what we observed, and for each of these we get a direction and a potential change of the velocity that we're looking after along the way. So as you can imagine, maybe we have quite a few terms now coming into play here, because we have the whole chain of operations and also the basically two components. We have the u being used multiple times, and we have the d being checked multiple times, a bit intuitively. Does that make sense? Critical. Oh. Oh. Okay. Make sense? Or not really? Very cool. No, what's unclear? A good question. So the question was, at which state do we use the new u? In a way, there's always just one u. There's not really a new u. So we do one chain. So it's good you're asking about this. We use the u one time, constant, through the whole chain. Then we get a step in u, we change it, but then we have a new u, and that's again used for the whole chain. So it's really, we do it once for all the way, then we change u, then we do it with that, the whole chain again. Right? So basically for the whole pass up here, it's always just the u. So basically also for what I show on the next slide, we only have one u. All we're interested in is you're computing this gradient of u, the step in u. After applying it, gradient descent or so, we have a different u. But for all I have on the slides, basically that doesn't play a role. It's always just one u. Exactly. We go through, or we apply this gradient, we get one gradient out at the right. I wrote it at the wrong side here. After going through the whole backprop chain, we got one step in u, and that we apply. Then we have a new u. With the new u, again, go forward, compute the loss, and so on. But the gradient in u is really this one update vector that we get out of the whole forward-backward path. And until we've applied the u, it stays constant. Because we actually cannot. The question was, why don't we do an update here? If you think it through, it's actually not that easy to do. You could compute some intermediate value and then restart, but what I'll show you next is actually the correct way of doing it. If you do something else, you would not get the right answer. So what I'm showing here on the slide is actually the full derivative, the full Jacobian of the forward-backward chain. If you try to get away with less, you would not get the right answer, basically. So, right, if I start modifying it somewhere in between, you might get something, but you basically don't get the right quantity out of it. So for this construction, for moving by multiple steps, computing an update, we really need to go all the way through all of these steps and just do one step at the very end. Otherwise, it's not correct, basically. Yeah, so the difficulty is now that for each of these steps along the way, if we are just looking at one step S along this chain, because of all the losses that were computed, we actually now get contributions from that one loss term towards all of the previous steps. So if we compute the loss at step S, that actually appears multiple times here, because mathematically we actually need it for every one of these steps. In practice, you would probably compute this only once. It's always the same term, so it doesn't change, but it just appears multiple times. We need to backpropagate from each of these, or we need to propagate the one loss towards each of the previous steps. So we need to basically go back from the loss to the S step, and we need to go back to the S minus first step. And we need to go back from the loss to the S minus second step. Or sorry, this S minus second I haven't even drawn, right? But I hope you can imagine, right? In two steps. And down here, we have basically the one that goes all the way to step 0. But this is really only for a single loss term in our chain. It influences all the previous steps. So for one loss, we're accumulating all the previous ones, which means we basically have something quadratic for the full one, right? So it's basically classic Gauss formula. So for basically if we do 3 of these steps, for the final one we get an influence for all of the steps, then we get for the next one we get so 2 remaining ones, for the last one 1. But in total, we'd already have 6 terms that contribute to the loss. I hope that looks weird on first sight, but I hope that makes sense. Oh. Nice. Not too useful without the chain. But here, it's maybe easier to draw, right? But if we just look at, say, the second step here, this loss actually goes back to the u one time here, and then also one time here. And the first one, well, kind of only goes back into the u one time here. But potentially each of these terms influences the whole chain before them. And then, if you add up all of these, you have kind of a triangular dependency matrix, and it's still essentially squared. So that is why even the simple case with a single u is potentially interesting, because also if you imagine now a neural network playing a role here, that would come up multiple times. These terms also would accumulate in a very similar manner and could potentially also lead to a pretty large number, quadratic number of terms. Yes? the question was, do we actually use this, right? It sounds very expensive with potentially many terms coming into play. Yes, we use this. And we've used this actually with hundreds of steps, potentially. You have a lot of terms. Again, what kind of saves us is that, well, these terms actually reappear as mentioned before. So actually also the second one, all of these repeat. And we always just need the contraction to a single vector. So there are a lot of terms, but if you go back step by step, you can actually typically just always collect these and collect them together in a single vector. If we need to store all these matrices, especially if we would store them multiple times, we would be lost. It would explode. But always compressing it into the minimum necessary information to these single vectors, it is actually feasible to do this. So I think that is an important message here, and it's not so obvious, but even for this seemingly relatively simple chain of a few steps, we potentially get a large number of these Jacobian terms and a large number of influences on some quantities to be optimized, like the velocity. Could also be a neural network, right? Oh yeah, you have the arrow on the slides as well, and right, we actually do get on the order of s squared updates for such an unrolling step. I do want to highlight this projection step next. So there was this part with the divergence freeness. This is now not explicit anymore, as was the advection, but now something that potentially involves more steps. Interestingly, or luckily, in this case and also in quite a few others, it's not even much more complicated. So the theory behind it is basically inverting this Laplacian that we also had on the slides before, or at least numerically approximating the inverse. The details actually don't matter too much. The important thing is basically you're constructing a matrix A. So we're solving some linear system. You can see this is AX equal to B, or in our case with our notation, it's basically A times P being equal to some right-hand side B, collecting these divergence, the amount of compression. And to solve this, what we're doing is, well, we're basically computing A inverse of A, B. And the main operation, also the costly thing, is this matrix inversion. Right? Typically, we can set up the A matrix relatively easily, but the A inverse, this is costly to compute. Now, what you could actually naively do is, I do have the whole construction here on the slides. Theoretically, you could take the same perspective on the solving process and say, well, here I basically, for the matrix inversion, I now have some computational steps. I treat this like with the P before, have a sequence of steps, and then I backpropagate through all of the steps. That would be correct. Mathematically, that would give you the right answer. However, if you're familiar with these conjugate gradient or multigrid solves, potentially you have quite a large number of these steps here. That would mean also in your forward chain, potentially you have maybe 100 calls of your solver, each of them involving some matrix multiplication, matrix vector operations. And backpropagating through all of them means we need to store the in-betweens, we need to compute all of these derivatives. It would be very expensive. We're dealing with a linear system here, right? We're actually looking for the derivative of this linear equation. And what we are now interested in the backwards pass is actually that we plug this expression into something else, right? You would have some outer operation, anything that follows up, basically using the result of that, the A inverse times B, and working on with it. But so what we are now interested in for the backwards pass is actually just the derivative of the P, or that expression, with respect to B. And what is the derivative of this expression with respect to B? I know my handwriting is not the nicest one, right? But this A is just a matrix. This is a linear equation, right? So if I take the derivative of that with respect to B, I'm basically left with my matrix. That's the A inverse. This is what we computed in the forward pass. It might have been costly. It was not easy to compute, but in the backwards pass, we actually need the same thing. Right? So this might not be so intuitive if you're familiar with these numerical solvers. In the forward pass, we're typically struggling in numerical methods courses. You're struggling, and it's our own science how to compute this matrix inverse. But from the concept of backpropagation, what the solver actually gives you, what something like a conjugate gradient solver gives you, is directly the multiplication of your right-hand side with that matrix. Right? You're actually typically not getting the A inverse out. That usually as a dense or potentially dense matrix could be costly, but you're basically computing the inverse matrix times the right-hand side vector, and the operation that we had in the forward pass is actually now exactly the same that we need for the backwards pass. So instead of backpropagating through all of these solver steps, what by now I think is also quite a common concept. Right here, just have this on the slides. So we can actually really reuse the same solver that we had in the forward step for the backward step. Right, so this matrix solve being linear, the same A inverse, and we actually need it at the same spot, right, at the state of our solve, appears both in the forwards pass and then also here for the gradient in the backwards pass. And you can actually, we have a few comments on the next slide. In a way, directly reuse any solver that you had to compute this quantity in the forward pass. You can simply call the same solver on the incoming vectors in this example from your loss. Could come from some other chain. Right? You basically get in the backwards pass some incoming vector, and then again you call your solver on that incoming vector to compute the same matrix inverse times vector here. Yeah, so that's the approach I've mentioned before. Theoretically, a solver is nothing but a chain of potentially hundreds of matrix vector operations. You could just code these up in PyTorch. Would work. You would get a gradient out of it, but it would be super expensive and potentially even numerically quite unstable. Because each of these operations would be registered and stored and backpropagated through. So this higher level view that I presented on the previous slide, you can actually see it as an implicit differentiation. Right, I don't want to go into the full write-up here, but this is an implicit derivative, right, of kind of looking at the high-level operation and computing the gradient also with the final quantity with the A inverse. And from that standpoint, and luckily also for an implementation, it basically means all you need to do is, if you have the solve in the forward pass, also call the solver again on the incoming vector for the backwards pass, and then pass the result on to the outer call. So luckily, this is relatively easy to do, and this implicit derivative calculation is actually typically a lot faster and also more accurate. So unfortunately, it needs a bit of thinking. You need to be aware of what happens in your solver. Depending on each of these steps, you might need to make some decisions, but in this case, luckily, it's actually relatively simple to compute the derivative if you have the solver. And you can, if you have a nice conjugate gradient or multigrid, then you also get the gradient quite quickly and efficiently. Yeah, so there are some examples on the website if you're interested in this for the burgers, for a simple PDE example without linear solves here. I can recommend taking a look, but it's actually a good time also to end this chapter. Are there remaining questions for the state? Okay. Yeah, thanks so far. Then next week we'll continue with a bit more of a discussion and in-depth examples of how to combine it with neural networks. Right? That's a big open question now. We've had a lot of topics on how to compute these derivatives, but no neural networks. That's a logical next step. So see you again next week.